Hi, I'm Thomas. In this lab, I recorded a projectile launch, extracted x, y momentum data in Tracker, and built two glow script models, one with gravity only, and one with gravity plus quadratic air resistance. I will compare both models to the experimental trajectory. The goal of this experiment is to see how well physics predicts the projectile's path. It is also to determine the importance of drag on projectile motion. Using the momentum principle, I update momentum based on net force. In Model 1, only gravity acts, but in Model 2, gravity acts alongside drag, where drag always points in the opposite direction to the velocity and scales with the square of speed. My group filmed the object in 2D with the camera stationary and used the calibration stick to set the scale in Tracker. The calibration stick was a meter stick in real life that we then could just easily align up with the blue line you see there to give a 1 meter calibration stick. I then placed the x-axis along the floor table and set the origin directly below the initial position as required. That is the reddish pink line you see covering my friend's body. Tracker output a time, x position, and y position for each point, each frame that we marked the center of mass for throughout the motion. From the earlier motion, I estimated the initial velocity components to be about 3.69 meters per second horizontally and 2.46 meters per second vertically. These values then became the starting condition for both the drag and no drag glow script models. In the gravity-only model, the net force is just weight downward. Momentum changes linearly in the y direction and the x velocity stays constant. This predicts the classic parabolic trajectory. In the gravity plus drag model, there's a little more complexity. I added a drag force that always opposes motion. Its magnitude scales with the speed squared. Its formula is Fd is equal to negative b v squared v vector, which is the vector v over the unit vector. I treat b as a fitting constant and adjust it until the predicted trajectory best matches the measured one. Here you can see the output is different to the gravity-only one, as both paths follow the same track, but you can see the ending data for the gravity-only is around 3.7, whereas the gravity plus drag ending x-coordinate is only around 3.4, where that drag slows it down and causes it to go backwards. Then the last question was, what if the ping pong ball was thrown upwards with the same speed? The answer is, if the object were thrown straight up with the same initial speed as in the experiment, it would take longer to reach the ground than in the original toss. That's because, in my original throw, only the vertical component controls the time in the air. If I had to redirect the same speed entirely upward, the vertical component becomes larger, so it rises higher and spends more time going up and coming back down. In the gravity-only case, the vertical motion follows yt is equal to y initial plus v initial t minus 1/2 gt squared, which is the classic kinematics formula, with the time to hit the ground being the positive root, t is equal to v initial plus root v initial squared plus 2gy initial over g, which increases as the upward launch speed increases. You can also look at this as just the quadratic formula. With drag, the straight-up case would still tend to take longer than the original, but drag reduces action speed faster and can reduce the total time compared to the no-drag prediction. In conclusion, the experiment trajectory matches projectile motion, but the ideal gravity-only model is not perfect because real objects experience air resistance. Adding quadratic drag improves agreement with the data, especially later in the flight. The main assumptions were 2D motion, constant gravity, and a drag force proportional to the speed squared. Remaining differences likely come from tracking uncertainty, calibration error, and the fact that the drag coefficient b is an approximation. Thank you, and that's it.